Okay, I think it's right. Okay, so yeah, so today we'll be doing some past paper questions because like last Thursday was holiday, so they didn't complete the syllabus today. This Thursday you will be completing the syllabus, right? Okay, so so we'll be going from back to front. So let's do the essay questions first, right? Okay, you all have read the questions, right? Okay, so that means I can just quickly Okay, so let's start with question number B2, right? Okay, so our task is okay, given an integer n, a positive integer n, and coins 1 cent, 5 cent, and 10 cent, and 25 cents. We want to verify if this strategy, where you always choose the coin that fits into the current value, and you choose that coin, and then you recurse with n minus that value, and then keeping on repeating this procedure. Okay, so will this lead to the optimal number of coins? That means will this lead to the smallest number of coins? Okay, so that is what we want to see. Okay, right. So if you just do some examples, you realize that it's hard to prove that it does not, right? Okay. Okay, so it's hard to prove that it does not. Okay, and actually, if you just think a little bit, it's very easy to prove that this is actually this will lead to an optimized solution, right? This will give you the least number of coins, right? Yeah, so this is very easy, right? Okay, so oh yeah, sorry, I forgot to bring my USB A to C adapter, so I cannot use my stick. So I'll use my phone. Yeah, so the first case, okay, right. So in this case, in this question, right now, so you're given coins 1, 5, 10, and 25, right? Okay, so if coins 1, 5, and 10 were given, right, instead of 25, okay, because 1 divides 5 and 5 divides 10, then you can easily prove that like this set of coins, which is 1, 5, and 10, will definitely be optimal solution. But the difficult part is 25 is also there. Okay, so that's the difference here, right? Okay, so let's make this easier. Okay, so first let's consider the case if n is actually less than 25. Okay, if n is less than 25. Okay, so now recall a greedy choice. A greedy choice was to pick the largest coin, right? That fits in the current target and repeat. Okay, right. So we want to show that doing the greedy step doesn't hurt optimality. Okay, so doing the greedy step doesn't hurt optimality. Okay, by the way, this is my line of thinking, right? So the props answer might be a little bit different. Okay, okay. So if okay, so first case, if n is less than 25, right? Okay, now you consider you divide that into 3 subcases, right? So if n is like between 0 and 5 exclusive, if n is greater than 0 and less than 5. Okay, now out of the 4 coins, which coins are choosable? Only $1, right? Right. So, but the thing is, now our greedy choice was to prove that you must choose the largest coin that fits into the current sum. You choose that coin, and then you replace your target sum by n minus value of that coin and repeat, right? But here the only coin is 1, and that also happens to be the largest. So any optimal solution has to use only 1 coin, right? And the largest coin is also 1. So therefore, our greedy choice of using the largest coin all the time is the same as the optimal solution, right? So this is the case. So because when n is greater than 0, less than 5, the optimal solution also has to use 1 coins, and our greedy solution also is 1 coins. So therefore, both are the same thing. Therefore, the greedy solution is optimal. Okay, right. Now, if n is at least 5 and stick less than 10. Okay. Now, what are the allowable? What coins can you use here? Okay, quickly you can tell. Only
1 and 5.
Only 1 and 5, right? Okay, so what's the larger coin? 5, right? So in the greedy choice, we would all because n is at least 5 and strict less than 10, the largest coin that can fit into this n is 5, right? Then what will the greedy choice do? It will choose 5. Okay, that's the first step. Okay, now consider any optimal solution that someone gives you. Okay, Now, if this optimal solution also chooses 5, then we are done. Why? Okay, so let's quickly ask questions, right? Because these are kind of easy questions. So, CS3230. Yes, William.
Because if you choose 5, you go back to like first case. 0.
Yeah, okay, that's true. But let's not use let's not think like that. Okay, so our grid choice was to pick the largest coin that fits into the current target sum and repeat, right? Okay, so that's a greedy choice, right? So in an optimal solution, if opt also chooses 5, then we are safe. Why?
Because it picks the same choice as you.
Yeah, so it makes the same choice as us, right? So even if you do your greedy step, I mean the possibility of hurting optimality is 0. I mean it's guaranteed that you will not lose optimality, because here there is a optimal solution that also uses coin 5. Okay, right. And of course, yes, then you go to a small amount and then you just repeat the argument, but that's fine. Forget about that for now, right? Okay, so if n is at least 5 and strict less than 10, if the optimal solution also use coin 5, then you're safe, because our grid choice was also to use the largest coin, which is 5, and both are doing the same thing, so we are safe, right? Okay, so suppose that the optimal solution didn't use 5, only use once. Okay, then we cannot say anything, right? Because the optimal solution is very complicated. It's something completely different from us, right? We chose the largest one, which is 5, and then we repeat the argument, right? But the optimal solution only use 1 coin. Now, so if you don't choose the largest point from 1, 5, which is 5, that means if the optimal solution didn't choose the largest point from 1, 5, can you be optimal? I.e., okay, so can you be optimal? Now, to help you answer this question, you must ask yourself, how many ones will you need to choose other ones? Yeah. You will. Yeah.
More than 5.
Yeah. So you need to choose n, right?
Ah.
Yeah. So and n is at least 5. Okay. So if you have at least 5 1 coins, then can you be optimal? Yeah. Why you?
Because you can always replace the 1 coins with 1 5 coins.
Yeah. You can replace 5 1 coins with a 1 5 coin. Okay. So therefore, you are decrease the number of coins in opt, right? So then can opt be optimal? No, right? Because opt wanted to choose the least amount of coins, right? And here we showed that in opt, if you swap out like 5 1 coins, so 1 5 coin, then you decrease the number of coins, right? So then can opt be optimal? Okay, just say. Can opt be optimal if you can reduce the number of coins in opt? No, right? You have to be confident, right? These are very easy questions, okay? Okay, yeah. So definitely, even in optimal solution, it cannot only choose 1 coins. Okay, it must choose at least 1 5 coin. That means it must choose at least 1 5 coin. But our greedy choice also was to choose 5 coin, right? Which is the largest coin. That means since addition is commutative, right? So you can bring the 5 coin to the 5 coin to the front in your opt solution, and opt is doing the same thing as you as the first step. Okay, so but doing the greedy step will not hurt optimality. Okay, so far so good, right? Very easy. Okay, if n is at least 10 and strictly less than 25, okay, then what are the legal coins? The only legal coins are 1, 5, and 10. Okay, so if n is at least 10, the largest coin that fits is 10. So our greedy choice will choose 10. Now we want to show that any optimal solution, if the optimal solution also chooses 10, you will not hurt optimality. Okay, because that's the greedy step. Okay, so suppose the optimal solution never chose the largest coin. Okay, now I'm not going to repeat the same argument. Okay, so if I'm not going to ask, what if the optimal solution chooses 10? That's the same thing as us. So we don't need to do anything. That's also optimal. If they're optimal, then we are optimal, right? We cannot hurt optimal. Suppose optimal solution never chose the largest coin. That means it never chooses 10. Okay, right. So it only chose what coins? 1 and 5, right? Okay, right. So since okay, now n is at least 10, strict less than 25, right? Okay, this one, right? Okay, at most, how many 1 coins can the optimal solution choose? How much? Can it choose? Okay, can it choose at least 5 1 coins in the optimal solution?
No.
Why? Yeah, you can choose one coin, right? You can choose one of the 5 coins to replace 5 1 coins, right? How many? Okay. Okay, so and then how many 5 coins can this optimal solution choose?
Oh.
At most, how many 5 coins can the optimal solution choose?
Oh.
Can it choose at least? Can it choose at least 2 5 coins? Yeah, right. So if the optimal solution chooses at least 2 5 coins, then you can replace 2 5 coins with 1 10 coin, right? So then can be optimal? No. Therefore, so therefore now the number of whatever coins that chooses, if we didn't choose 10 is 1 and 5, right? Number of 1 coins must be strictly less than 5. That means at most 4. Number of 5 coins must be strictly less than 2. But then with those constraints, what's the largest value you can make? 9, right? So then can it make at least 10? Let's say, can you make at least 10? No, right? So then that's a contradiction, right? Okay? Okay, right? Okay, so therefore it can't make at least 10. Therefore, it has to choose 1 10 coin. Okay. So the line of reasoning was, we suppose that it didn't choose a 10 coin and we came at a contradiction. Therefore, it must use at least 1 10 coin, which is the largest coin out of 1 5 or 10. And greedy also do the same thing, and Opt also has to do the same thing. So we can see. Okay, so those are easy questions. Easy part. Okay. Now come to the case n is at least 25. Okay. Now it's very weird because when I wrote this, I put everything close together, so I can't so I just zoom it. Okay, so now if n is at least 25, now take any optimal solution opt. So we want to show, now since n is at least 25, what's the largest point that fits into this n? 25, right? So the greedy choice will always choose, for the first step, it will choose 25. Okay. Now we take any optimal solution OPT. If OPT also chooses 25 as the first coin, then that's also doing the same thing, greedy also doing the same thing. So we are safe. Okay. If OPT didn't choose 25, now we want to show that it's not possible. That means we want to show that opt has to choose 25. That means our big choice has to be safe. Okay, we want to show that opt, if n is at least 25, opt must choose 25, at least 125 coin. Because, and then if we can prove that, opt has to choose at least 125 coin, then we are safe. Because why? Our grid choice also is the first step is to choose the largest coin, which is 25. So opt, because addition is commutative, you see then in the collection that opt chooses, 25 is there. So you bring 25 to the front. So in the first step, opt also chooses 25, you also choose 25. So you are safe. Okay, so grid choice is same. You want to prove that 25 must be there in this collection that opt chooses, right? Okay, right. Okay, yeah. So here, these are easy questions. If opt also choose the largest coin, we are done. Same reason as before, because we are also in the greedy step. Opt also chooses to do the greedy step. Okay, so now suppose that opt never choose 25. Okay, now again, next, at most, how many 5s can you choose? 1. Because if opt chose at least 2 5 coins, then you can replace 2 5 coins with 1 10 coin. This is a condition. Okay. Okay, so 2 cases, right? So we want to analyze the case where the number of 5 coins is 1 and other cases number of 5 coins is 0. 2 cases, right? Okay, so let's analyze the first case. If number of 5 coins is less than 2. Okay, so now if the number of 5 coins is 1. Nicholas, right? Okay. So if the number of 5 coins is 1, so we have 2 cases to consider, right? So number of 5 coins is either 1 or 0. If the number of 5 coins is 1, then at most how many 10 coins can you choose? 1. Okay, Nicholas. Did I say Nicholas? No, right? Okay, maybe okay, Nicholas. Yeah, you can also explain your reasoning then.
At most, how many 10 coins?
10 coins. If the number of 5 coins that opt has chosen is 1, because we know that number of 5 coins that opt chooses has to be at most 1, right? So either 1 or 0. So first case is it chooses only 1 5 coin.
Then you can only choose 1 10 coin.
At most 1 10 coin.
Yeah.
Okay, what if it chooses at least 2 10 coins?
Then it contributes because you have one 5 coin and two 10 coin, so you can replace it with 125.
Yeah.
10 coin.
Yes, correct. Okay, so that means if Opt has chosen 1 5 coin, then it can only choose either 0 or 1 10 coin. Okay. Now, then you consider, now you think about this, right? I have written down here, but fine. So the number of 5 coins is 1, right? And the number of 10 coins is either 0 or 1, right? So what is the largest value you can make from the 5 and 10 coins? Or rather, can you give me a strict upper bound on the number on the value that you can make using the 5 and 10 coins? Yeah.
15.
Is it yeah, 15, 15, right? Yes, 15. So 5 plus 10, right? 15.
Yeah.
So 5 plus 10 is 15, but 15 is less than 25.
Yeah.
But the value we are considering is
more than 25.
Okay, so to get more than 25, the only other coin you can choose is
25.
No, we suppose Opt never chose 25.
Oh.
So in Opt, if Opt wants to get a value at least 25 and he chooses only 1 5 coin, then he must so we consider like this, right? So if Opt chose only 1 5 coin, then the number of 10 coins he can choose is at most 1. So the largest value we can make using 5 and 10 coins is 15, at most 15. But you know that Opt has to make at least 25, right? So he has to go beyond 25, right? So the only other coin he can choose is
1 coin.
1 coin.
Yeah.
But that means there is a sub collection that adds up to 25, right?
Yeah.
Why?
Wait, sorry.
So there is okay. So
there's a sub collection.
There's a sub collection of coins in Opt that adds up to exactly 25.
Then it's not optimal because you're just
okay. Yeah, that's true. Yes, yeah. But I want to know. I want to tell me why is there a sub collection that adds up to exactly 25?
Oh, there's a sub collection
of coins in Opt that adds up to exactly 25.
You're just choosing multiple 1 coins.
So
then it's just not optimal. Because the sub collection can also be reduced to the base case also.
Okay, so I want to think like this. Okay, so now the largest largest value we can make using 1 5 coin and at most 1 10 coin is 50.
Yeah.
But you need to make now but Opt will make a value of at least 25. That means the only way he can reach at least 25 is now you add 1 1 1 1 1, right?
Yeah.
So that means from like a value that is at most 15, you add 1 1 1 1 until you get at least 25, right?
Yeah.
So then at one point you keep on adding ones until you hit 25, right?
Yeah.
So then that collection add up to
25.
Yeah. So then you can replace all that coins with
125.
So then it is optimal?
No.
No, right?
Yeah.
Okay. Yeah, that's the reason. Okay, nothing much, right? Because here, right? Here, see, but that means the number of 5 coins times 5 plus 10 times the number of 10 coins times 10 is strictly less than 25. But we need to make a value of at least 25. But from strictly less than 25 to at least 25, the only value coin you can use is 1. That means you keep on adding 1 1 1 1, but at one point you will hit 25. And that sub collection will be 25. So you can replace it with 125 coin, and that's a condition. Okay? Easy, right? Next one. Okay, so we'll consider next case, right? So if the number of 5 coins is 0. Okay. Right. So if the number of 5 coins is 0, okay, so because we had 2 cases, right? The number of 5 coins is strictly less than 2. So the first case is equal to 1, then the other case is 0. If the number of 5 coins is 0, then at most how many 10 coins can you choose? Yeah, Shaoshen. Oh wait, Christopher, right? Yeah. Where's Christopher?
At most 4.
At most
4.
12. At most 4. You can just tell me. At most, how many 10 coins can you choose? If you have 0 5 coins.
4.
I can't hear you. You just show it with your hand. Show with your hand. Like
4.
Okay, yeah, correct. At least 4, at most 4. Why can't you choose 5?
Because if you do 5, you can replace it with 2 25 denominations.
Yeah, correct, right? Yeah. So yeah, that's right. So if you have 0, 5 coins, now 0 is now 5 is out of the question. Only you can choose 1 and 10 coins, right? Because opt never chose 25. Then you can only choose at most 4 10 coins. Because if you choose at least 5 10 coins, then like 5 10 coins will add up to 50. But you can replace 5 10 coins with 2 25 coins. So therefore it's a condition. Okay. Now take note that n is at least 25, right? Okay. Okay, now again I ask you, at most how many 1 coins can you choose? Yes, Shamshin, right? At most how many 1 coins can you choose?
4.
Yes. So solely with 1 coins, what's the largest value you can make? So solely, I mean only using 1 coins, what's the largest value you can make?
4.
4. But your value is at least 25. So now you know that number of 5 coins is 0, right? So the only other coin you can use is 10, right? So at least how many 10 coins would you have to use?
4.
Okay, so our value is at least 25. Now we know that with 1 coins you can make a value of at most 4. But you need to reach a value of at least 25. So how many 10 coins should you use?
3.
Yeah, you need to use 3, right? So at this point we know that if you use 0, 5 coins, the number of 10 coins is at least 3 and at most 4. Okay. Right. Yeah, okay. So if you use 3 10 coins, is there a way to make 3 10 coins using 25 coins, but you use less than 3 coins? So the first case is it uses 3 10 coins. The other case is it uses 4 10 coins, because we know that either 3 or 4, right? So if you use 3 10 coins, is there a way to make 30, because 3 times 10 is 30? Is there a way to make 30 using less than 3 coins?
Yes.
How?
25 and 5.
Yeah, so that's 2 coins, right? So can opt be optimal? No, right? No, right? Okay. What if opt uses 4 10 coins? So can you make so can you make 40, because opt uses 4 10 coins, so 40 is a summoned in this sum, right? So can you make 40 using less than 4 coins? How?
125, 110, 1.
Yeah. Okay, so that means you use 3 coins to make 40, but opt uses 4 coins to make 40. So therefore opt is not optimal. That's a contradiction again. Okay, so every contradiction arises because we suppose that okay, so let's ask someone else. KJ, right? Yes. So why did every contradiction arise?
Sorry.
Yeah, so we arrived at many contradictions, right?
Yeah.
So why did they arise?
Because the greedy solution is correct.
No. No, we are just analyzing the optimal solution. Anyone else want to try?
Because we assume the
Wait. Anju, right? Anju, you are present twice, right? You are present twice, right? So I will ask those who haven't present. Brian? Arun? Yeah, so now we suppose that number of 5 coins is 0, right? And so we have these cases, right? 10 coins is either 3 or 4, right? So each of those cases ran into contradiction. Why?
because there's always a better case where you can use 25, but our original assumption was that we cannot use 25.
Yeah, so the way that we began the proof is to suppose that opt never chose 25, right? And everything ran into contradiction, right? So therefore opt must use 25, right? Okay. So our greedy choice is also to choose the largest coin, which is 25. So that means opt also needs to use 25. The greedy solution also is 25. So therefore you and the optimal solution are doing the same thing. So therefore there is no. Yeah, that's it. All right. So you can see, I mean, this is easy question, but okay, it took a little bit of time for me to solve, but I solved it. But I was just like playing around. So okay, so yeah, so hope you got it. This is quite easy for the question. So it's not like related to 3230 at all. Just like general knowledge, right? Should give it to my cousin. Okay. Next question. Okay, so B1. Okay, so you all have read the question, so I'll just summarize it. So you have like at least 3 houses and you have 3 children. The parents want to divide the houses among the children such that each child receives at least 1 home. Okay, non-empty block of consecutive homes, right? And each child has a positive integer value for each house, and the child's value for his or her block is the sum of values for each house in that block. Okay? The parents want to divide houses so that the sum of the 3 children's values for their own block is the highest possible, right? Okay, right. So okay, so like this, right? Okay. So I'm gonna ask a question here, right? Simple question from Nathan. Yeah. Okay. So now you understand the question, right?
Yeah.
Okay. So now I'm going to ask you a question, right? So if I can solve the problem, so now here, right? If you look at the question properly here, right? So you see that the parents want to divide the houses among the children in such a way that each child receives a non-empty block of houses, right? Now the thing is that this order A, B, C can be switched, right? Either A comes first, B second, C is third, or C comes first, B comes second, A comes third. So we just need to allocate a contiguous block of houses, right? So I mean, A, B, and C can be mixed, right? Okay. Okay. So my question is this, right? So if I can solve the problem for the fixed order of Aisha, Bob, and Charlie, that means A, B, C, in theta Fn time, then I can still solve the general problem in theta Fn as well. Why?
Because allocating it is passing Fn, then we have 6 permutations, right? Then since each uses Fn time, then 6 times Fn is also Fn.
Yeah, correct. Yeah, that's correct. So yeah, so if I can solve the problem for a fixed order of ABC, then I can simply brute force like the 6 permutations, right? Because 6 is a constant number. So even if I do it 6 times, so 6 times Fn is still theta Fn, right? The constant. So yeah, so if you can solve it for like ABC, then you can solve it for any order because you can just brute force all the other permutations and just take maximum out of everything and you're done. Yeah, so okay, so now that we know about that, we just need to solve it for one fixed order and then just like do the same thing for every like 1 of 6 orders, right? Okay, so let's consider one order. Let's consider ABC, whatever, right? ABC. Okay, so here we have a illustration, right? So ABC. So here, suppose you have 10 houses, right? And so Aisha has 10 values, and Bob also has 10 values, and Charlie also has 10 values. So what's done 4 to 6 1? CS 4 to 6 1. Who's in year 4?
I haven't took 4 to 6 one.
No, everyone is in year 3. Everyone is year 3. You should take 4 to 6 1 in year 4 7 1. Okay. It is actually quite an interesting module. It's called algorithmic mechanism design. It talks about like real life problems, very applicable. I think out of all the CS mods, the one that is really applicable is like 4 to 6 1. You can like go and talk with like people who are not in CS and just explain stuff to them. Like 4 to 6 1 is like very interesting. You should, if it's possible, you should take it. Very interesting module. Also, Prof. Farooq is teaching. Okay, so you have Alice, Bob, and Shah. So Aisha, Bob, and Shah, right? So we have 10 houses, and we have so each of them provides their own valuation for the 10 houses, right? Okay, so now we want to allocate a contiguous block for Aisha and then Bob and Charlie. Okay, so an allocation like that would look like this, right? Oh, okay. Okay, so an allocation like that would look like this, right? For example, we can give these houses to Aisha. We can give these houses Oh, yeah. Okay, I can give these houses to Aisha, and then I can give these houses to let's say to Bob, and then give these two houses to Charlie. Okay. Okay, so let's actually recast the problem. Let's look at the problem different way. Okay, so in this 2D grid, we just need to find a path like this that maximizes the sum of values around the path. Okay, so essentially we want to find a path like this that maximizes the sum of values around the path. Okay, so now I just realized that I made a little small mistake, right? So can someone see? Yeah. Yeah, can someone see? I made a small mistake when I now want to realize. Yeah. Can someone see?
Some of them have overlapping.
Yeah, this one, right? Okay, so I made a small mistake, but if you know how to solve the problem for maximal path like this, you also know how to solve a problem like this. Okay. Because you just need to skip this house. Okay. Okay. I'll get to that point in a bit. But okay, let's try to solve this problem. In this 2D grid, we need to find a maximal like staircase path like that. Okay. And then this equivalent to solving the previous problem. Okay. So assume that I didn't color this, right? Assume that I didn't color this. So if I solve it like that, so if I find the maximal staircase path like so, then that's the same thing as solving the previous problem. Okay, is that this also kind of reduction, right? So if I can find a maximal, okay, so suppose someone gives me this grid, right? If I can find a maximal path, staircase path like so, out of all such paths, right, that goes like that, right? Then I will solve the previous problem. Okay, is that okay? Right? Because essentially that's the same thing as previous one, right? Okay. Okay, so here, yeah, I realized I made a small mistake. I actually considered both of them. But okay, let's solve this problem, and then if you know how to solve this problem, the previous one is also easy because you just need to skip this out. That's it. Okay, nothing much. Okay, let's start solve this problem. So we are given a 2D grid, right? And then we want to find a maximal staircase path from the start to finish. So it can either be like this, or it can either be like that. Oh, sorry, no, wait. It can either be like this, or it can be like that. Or what? It can also be like so. Okay. But there are some restrictions to this like staircase path. We want to ensure that at least one element is selected in each row. Why is that?
Each child will receive one and receive not one.
Yeah, that's right. So because we want to also ensure that each child receives at least one house, right? So we also need to ensure that Aisha gets one house, Bob gets one house, and Charlie gets one house. So we need to ensure that when you consider this staircase path, we need to ensure that you must choose at least one element from the each row. So you can't. It's basically you can't have paths like this. Okay, like you cannot have paths like that. You cannot also have paths like this. That's not a valid path, right? So you need to find from this place to that place, but you need to ensure that at least one element is selected in each row. Okay, right. Okay, so very simple divide and conquer solution, right? Nothing to think at all. Okay. Yeah, probably this is the easiest question in the exam. Okay. Function f row comma column. Okay, so let's just solve this directly, right? We want to find the maximal such staircase path. Okay, so base case. If the column is n, and the row is not 3, so if the column is n and the row is not 3, that means you are here or here. Then what can you tell about this path that we created? Task. I think we asked everyone, right? Except Brian is not here. He's done. Yeah, Keith is not here, right? Okay, anyway. Yeah. So anyone can tell. So if the column is n and we are not at the third row, then what can you tell about the solution?
Invalid.
Sorry? Yeah, it's invalid. That means your path ends either here or it ends somewhere or it ends here, right? But why is it invalid?
Because everyone should have at least one house.
Yeah, everyone must have at least one house. So in this case, Charlie doesn't have a house, right? Therefore, this solution is invalid. That means you need to prevent this solution block from being selected, right? Because by maximizing, then our output for this case would be So if we hit this case, then what should be output as the answer to F row command column?
Negative infinity.
Yeah, negative infinity, right? Because we need to prevent this solution from being selected, right? Because we are maximized, right? Okay, because you can prove that there's at least one such valid path from A to C, this point to this point. So since there's at least one path, then the maximum value is at least strictly greater than, like, let's say 0, because if they're positive integers, so negative infinity will never be selected, right? Okay, so if the column is n, right? Else, right? So else if the column is n, then where can we be? So if we didn't meet this case, that means if the column is n and row is not 3, that means we are here, right? Now if we didn't hit that case and we are here, now if the column is n, then where are we? Yeah, so we are here, right? Okay, so then the answer is simply m3 comma n. Okay. I mean, you can assuming that this array is m, right? So it's just written m3 comma n, row comma column. Okay, right. So next one, if the row is 1 and column is 1. So if the row is 1 and column is 1, okay. So we need to give this house to Alice, right? Definitely. Therefore, there's only one way to do this. So we need to give this house to Alice. We give this house to Alice, right? And then we recurse on F row col plus 1. That means we recurse from this point onwards, right? Okay. Yeah, so it's very straightforward, right? Else if row is equal to 1. So if you didn't meet this condition, and now you are meeting this condition, okay, this condition. Now where are you in this grid? Where are you in this grid?
A2 onwards.
Yeah, so A2 onwards until A9, right? You cannot be A10 because if you are in A10, you already hit this base case. So you're either one from here to here, right? Okay, so from this case onwards, we need to find the maximum path from here to any point in here to C10, right? So then all the very easy, right? Either so you have two cases. Either you give this house to Alice, or you give this house to Bob, and then you recurse, right? Okay, right. Okay, so here's where I made the small mistake, right? Oh, I did make a mistake. Okay. Yeah. Why is that? Okay, no way. Okay, so here, right? If row is 1, that means you're from here to here. Okay, maybe I drew it wrong, but I thought about it and I did the correct thing. Okay, so here, right? So if row is 1, then this is giving the first house to this is giving the current house to Alice, right? So there are two cases. Either you give the current house to Alice, or you give this house to Bob, and then you recurse, right? Okay, so if you give to Alice, then what happens? You give m row comma call to Alice, and you recurse on F row comma call plus 1. That means you stay on the same row. That means you go to the next column. Okay, right? Else you finish allocating to Alice. That means you give this house to Bob. If you give this house to Bob, then that means you must add m row plus 1 comma call. That means Bob's valuation. Okay, row plus 1, but the same column, right? Okay, so you need to add the valuation of Bob. That means m row plus 1 comma call. That means the next row but the same column. Okay, that's Bob's valuation. So you add it plus you recurse F row plus 1 call plus 1. That means like this. So you are here, but one case is allocate this to Alice. The other case is to remove this from to not allocate this to Alice, but allocate this house to Bob. But you recurse on from this point onwards. And so that would be row plus 1 call plus 1. Okay. The next one similar, right? Next one is we are at row 2. Okay, so row 2 means we are on somewhere out here, right? Okay, so we are either from B2 to B9, one of these values, right? Okay, so also again same thing, right? So either you can give this house to Bob, and then you recurse on the next column, next value in this row, or you give this house to Charlie, and then you recurse on row plus 1 call plus 1. That means the next house to Charlie. Okay, let's do this slowly, right? So for example, if you're here, right, either you can give this house to Bob, or you can give this house to Charlie. So if you give this house to Bob, then what happens? Then you need to add the valuation of Bob, right? Here, right? So that would be M row comma call plus F row call plus 1. That means you give this house to Bob and you recurse on the same row, but the next item in the row. Or you give this or you just stop giving this house to Bob, but you give this house to Charlie. And then you recurse on this part onwards. That would be what? M row plus 1 call, and you recurse on F row plus 1 call plus 1. So diagonally, right? Else you're in row 3. If you're in row 3, you have no choice but to keep on like allocating the same house to Charlie, because you have already done everything for Alice and Bob. Nothing to choose, right? That means M row call plus F row call plus 1. Same row, but you recurse on call plus 1, call plus 1. Okay, that's all. Yeah. So the code is correct, but my illustration is wrong. So it must go from here like that. That's it. Okay, done. So as you can see, you can recast your problems into any other form and then just solve them. So these are reductions. Like even if you don't realize, these are reductions, but very easy to actually reduction. Okay. Yeah. So next thing is that you should realize that there are overlapping subproblems, because you can reach, for example, you can reach what F row comma call. Let's say this value. You can reach this value in multiple ways. For example, you can reach it like that. You can also reach it like that. You can also reach it like that. So there are overlapping subproblems. So so if you have a divide and conquer solution that has overlapping subproblems, then what should you do? What should you do? You use memorization, right? Or convert on DP. Okay. Yeah. So you know how to convert this into DP, right? So you can just memorize here, right? Then nothing much, right? So CS111 and stuff, right? Or else you can just do bottom up DP, whatever you like. So if I do memorization, okay, if I do memorization and I memorize it and I get a DP solution, right? Then my function is A. How many states do I have in this my DP solution? How many states do I have? How many subproblems do I have? 3n. So row can take how many values? 3 values. Call can take how many values? N values. So therefore 3 times n is 3n. So there are 3n subproblems, and each subproblem can be solved in how long time? What time? Each subproblem can be solved. For example, if I call f4, 5, how fast can f4, 5 be solved without considering like recursive calls? That's the immediate work time. So essentially, I'm asking what's the time complexity of this work here without recursive calls. Is that a trick question? No, right? So I'm asking like if I call, let's say for example, f4, 5, right? f4, 5. So what's the time complexity to run the body of the function? Because that's the time taken to run, time taken to solve one subproblem, right? It's theta 1, right? There's nothing here, right? I mean, there's literally nothing here. There's just if conditions here, right? So the body takes what theta 1 time to run, right?
Yeah.
And then there are how many subproblems? 3n. So then total time taken is theta n. So the entire DP solution runs in theta n time. That's linear. I mean, essentially that's a fastest you can get, because you need to at least look at values at least once, right? Otherwise, if you didn't look at the values at least once, then how do you even start the problem, right? So you must take omega n time, right? So if you take omega n time to solve the problem anyway, and then you solve it in theta n time, so you're clearly optimal. Okay, because you need to look at the values at least once, because assuming that they're presented to you one by one, right? I don't know if they let you like store the values in one go and you can operate it by yourself. But anyway, so these are considerations that you can think about. But anyway, so this is answer theta n time. That's all. Nothing much. Okay, so it's some very easy MC questions. Some are like very easy. I think everything is quite easy. So consider following 4 statements. Is n in theta n plus 3230 is n in O of n plus 2? Yeah. Is n in O, theta of n plus k where k is a constant? Is n in O of n plus k where k is a constant? Is n in omega of n plus k where k is a constant? And is n in little o of n plus k where k is a constant? Yeah, who can tell me? Yeah, someone can just tell.
N is in theta.
Okay, so this is theta, fine.
And theta implies that is in big O and
Okay.
omega also.
Yeah, how about this one?
No.
Okay, so n is not in little o of 3 to 3 plus n is not in little o of n plus 3 to 3, okay? Because that is saying that this constant is little is like negligible when k goes to infinity, right? When n goes to infinity. Is that it? So you're saying that n grows slowly than n. So that you're saying that n goes strictly slower than n, which is the causation. So I mean, in the exam, you try to use your intuition, right? Don't try to like prove everything. I mean, of course, proving everything has merit, but you know that you also have very low time. So obviously, this wrong, right? So this wrong. So obviously, correct ones are these things. So 3 are right. Suppose that Fn is in this one and Gn is in this one. So what is Fn dot Gn? Okay, so now we know that by definition of theta n, Fn is at least C1 times n to the 5 to the n, at most C2 times n to the 5 to the n. So this is at least 0, and Gn is at least d1 n square 3 to the n, at most d2 n square 3 to the n. Then you know that Fn times Gn is at most C2 d2 times n to the 7 6 to the n is at least C1 d1 n to the 7 6 to the n. So therefore, Fn dot Gn is in
D.
yeah, n to the 7 6 to the n, right? So just multiply this, right? Very easy, right? This one is very interesting question. If I see this question, I would skip this in the exam and come at the very end because I think it's like a waste of time. I mean, if you can spot some interesting patterns, then please do. Okay, don't take my advice, it's bad advice, okay? So if you can see some patterns here, then please do, okay? I was a bit lazy to solve this question, so I just put interesting and I skip it. Okay, no, I'm serious, right? So in the exam, right? Please don't skip questions, right? If you find that you can solve it, I mean, for me, it's like too many values to look at. So yeah. So in the exam, if you can solve it, just quickly solve it and then go on. But in the exam, what I will do is like I'll come to this question at the end and so on. Because like there are more interesting questions to solve. Okay. Next one, fraction knapsack. This okay, so yeah, so same thing as before, right? How do you forget about this question, right? How do you solve a fraction knapsack? You order the values in decreasing order. You did this, right? Yeah, you should do this, yeah. So how do you solve fraction knapsack?
Greedily, yeah.
Yeah, agree. Yeah. When I say fraction knapsack, it has to be easy.
Yeah.
Yeah, so how do you solve fraction knapsack?
You just get the ratio of the value against the weights, and then you just pick the highest one all the time till.
So what I do value? Value over weight or weight over value? Yeah, so value.
Value is to weight. Value per unit weight, right?
Okay, so I did a mistake here. So yeah, so you order the values from highest value to weight ratio, and then so you order from decreasing of value to weight ratio and choose as much as you can from the highest value to weight ratio, and then after you pick everything, you can choose next value to weight ratio one, and then pick as much as you can, and then keep on doing the same thing, right? So out of these items, the highest value to weight ratio is 11:10. This one, and the next highest one is 90 to 19. So you can just choose a maximum amount of this one, and then choose a fractional value of this one, and just give this, right? Yeah. So this would be highest value to weight ratio, right? So this like should be value to weight ratio, right? Next one, suppose you have alphabet, this one with frequency, this one. What is average bit length of an what is average bit length of an optimal prefix field code? Yeah, so this Huffman, because we know that for any uniquely decodable code, nothing can beat Huffman in terms of the average length. Okay, so use Huffman. You guys learned Huffman, right? Undergrad, right? Yeah. So you construct the Huffman tree and then realize that the answer is 2.25.
Okay.
Anyone who has done 3236? Okay, so that's an interesting module as well. So please do it if you can. So you learn about like so you learn about how Huffman is optimal, and there is no uniquely decodable code that can get an that can get an average length strictly less than Huffman's one. And then you can also prove that the length of Huffman is like at least the entropy of the alphabet strictly less than h of x plus 1. Hx is the entropy of this alphabet. Okay, so you can take 3236 to learn about that. But this is not 3236, so let's just continue, right? Suppose that for changes I, the probability of getting an input length I is equal to the minus I plus 1, minus bracket I plus 1. And the probability of getting an input of length 0 is 506. What is the expected length? Okay, very easy. Expected length is this, and then you can expand 0 times 506 plus the summation. So after you do some maths, you can get 1/4. But if you have a calculator, just because it's MCQ, right? Just like approximate this value, use your calculator and get the answer right. Don't need to waste time with the exam. But if you have some time, if this comes as an essay question, of course you must slowly work out this sum, right? Okay, you can write this as I over 3 to the I plus 1 and do it from there. But since it's an MCQ, to save time, just type this value into your calculator and just get the answer. And it's good to write down the answer. Okay. But again, if it is a question, please do this format, right? Okay, so suppose the performance equals of n operations, ith operation cos I if I is the power 3 and cos I otherwise. Okay, so if you consider the cost of all operations, that means the sum of all the costs, then what can you have? So how many powers of 3 are there until n? Roughly log n, log base 3n, right? Okay, because that's the highest power that fits into n, 3 to log 3n. Okay, there's a flow here, but forget about that, right? So roughly log 3 n many powers of 3 fits into n, right? How many of those powers? So then if you sum up the cost, then you get what? 3 to 0, 3 to the 1, 3 to the 2, until 3 to the log 3n. Okay, and plus we know that if it's not a power of 3, it just costs 1. So how many other operations are there other than powers of 3? So if there are log 3n many powers of 3, then there are n minus log 3n roughly operations that are not powers of 3. Right? Each of them costs 1. So then you add this much. Okay, so just sum them up, very easy. So use geometric series and then you have n minus log 3n here. And then you find out this is that theta n, then average cost is theta n divided by n is theta 1. Okay, so then the answer is theta 1. Okay, so very easy. Consider algorithm that performs sequence of operations. Suppose that the worst case time for performing. Okay, suppose that the worst case time for performing an operation is Fn. Okay, and the worst case time for performing all n operations together is Gn. Okay, so then clearly, I mean, this is not even a question. I don't know why this is a question for this paper, but clearly, of course, n times Fn, because Fn is the worst case for any operation, then surely n times the worst case for any operation is the upper bound for the worst case time for performing all operations. Okay? Because I mean the worst case time for all operations is a value, that's fine. But each operation is upper bounded by Fn. So if you add Fn like n many times, then surely that G n is upper bounded by n times Fn, right? Okay. Okay, so I don't know why this question is there in the exam. I guess 3 marks. Next one, suppose that for some problems x and y, if x reduces to p, so if x carb reduces to y, then which of the following is true? Okay, if x carb reduces to y, then will y carb reduces to x necessarily? Okay, if this happens, then what can you do? Then surely there will be no conjecture about P versus NP, right?
I mean,
So you didn't.
we haven't been taught that yet.
Oh, yeah, sorry.
Lecture, yeah.
Yeah, so like, okay, yeah, okay, so if this is that is magical, okay, if you tell me that you can reduce x to y, but then that also means that y reduces to x, then there's no conjecture called P versus NP, right? Then that means everything can be solved in polynomial time, right? Okay, so you learn that on Thursday. Fine. Okay. Okay, so next one. If x reduces to y and y reduces to z, then surely x reduces to z by transitive, right?
Yes.
C. So that's correct. See, if x is poly time solvable, then so is y. If that is true, then again P versus NP, there will not be a condition. That means P will be equal to NP. Okay, you also learned that on Thursday, but yeah, these are done. I mean, this is like stupid, this is stupid, right? So the correct one is B, which is like correct, transmitting. Yeah, right. That's literally. So as you can see, it's I mean, it's quite an easy paper, so pretty much. Okay, yeah, so that's it for today. So let me just take, so everyone presented except Ryan. Ryan is not here, right? Yeah, everyone else presented, right? Yeah, so let me take the names, right? Gary? Gary is here. Even is here. Keith is not here. Gwynplaine is here. Ichul actually not here. Anand is here. Brendan is here. Ella is not here. Nathan?